Welcome to Lecture 4. We are going to continue on with our study of counting particles, and we're going to figure out how to do average atomic masses. Where do those numbers that are not whole numbers come from on the periodic table? We're going to revisit chemical formulas briefly. We've already done quite a bit with that before this lecture. Then we're going to get into what a mass percentage is, which is just a percentage, and then empirical formulas to finish us up. And then we'll be ready after this lecture to get right into stoichiometry, which is going to take us where we left off before ed midterm with balanced chemical equations, and we're going to add this mole thing to it. But not to worry, not a whole lot of new, just going to be numbers that you're not used to working with. All right, so anyway, that's the next lecture after this one. So we're going to talk about average atomic mass. How do we end up with those numbers on the periodic table that are not whole numbers? Well, the reason they're not whole numbers is because they are weighted averages of the different isotopes. So the way that we do that is we're not going to add up the isotopes and divide by the number of isotopes. It's a little different. A weighted average is when you take the mass of an isotope and you multiply by its percentage in decimal form, plus the weight of the second isotope times its percentage in decimal form. So here's an example. Magnesium has 3 naturally occurring isotopes, and here are their masses. Now, when we did isotopes, we talked about mass numbers. And now you're going to see masses for isotopes that are not whole numbers like a mass number. And there's a reason why. It has to do with Einstein's famous E equals mc squared equation. We actually lose a little bit of the mass, so the mass number for this isotope is actually 24, and this one is 25, and so on. We're losing a tiny bit of mass to create the binding energy needed to hold that nucleus together. Remember, those protons don't like each other, so it takes a lot of energy to hold the nucleus intact, and it's that energy we release when we make nuclear weapons and use nuclear power. So remember, tiny little living space, awesome power. All right, now we've got the abundances for those isotopes. So this one here, 23.99, has this abundance, or it's this percentage in nature. So we take that mass times that percentage in decimal form. Next isotope times its percentage in decimal form, and so on, and we just add them up. All right, so here is one problem. Okay, so let's copy that one and bring it into our writing program. All right, so they're telling us that silver has 2 naturally occurring isotopes, 107 and 109. And then it's asking you, so those are the mass numbers, what is the atomic mass of silver? It is 107.8682. Now, when you do these kinds of problems, it's really best to carry the decimals out pretty far. All right, 8682. All right, so that's the answer to A. And then they give you for isotope number 1, they give you the percentage and want you to figure out the abundance of 109. So this is a little algebra problem. So the two together add up, times their abundances, add up to the 107.862. So 107.8682 is what they add up to. Now they're not giving us the exact masses here, so we're just going to use the 107. So we know that 107, and we know its abundance, and we know we're going to add it to the 109, but we don't know its abundance. Now, what do these abundances add up to? What do the percentages add up to? Well, the percentages add up to 100. The abundances are going to add up to 1. So this is going to be, so really, we can solve this without using any x's, because 1 minus 0.5184 is the abundance of the other isotope. And there, again, that is because the percentages add up to 100, as all percentages do. And since we use them decimal form, when you put them in the equation, they add up to 1. So 0.482. And I guess you could have put x here, or we could have just answered that question as 0.482. Now they're giving us in the next one some exact masses. and you're having to figure out the exact mass of this because we just got this. All right, so in the next one, they're going to add up to that. The actual real mass of 107 is 106.905 times its abundance plus X, I don't know the exact mass of 109, times its abundance. Don't really have to put that in parentheses, and they all add up to the mass that's on the periodic table. All right, so I'm going to multiply this term right here so that I can bring it to the other side. And that comes out to 55.4 plus 0.482x equals the 107.8682. All right, so I'm going to subtract the 55.4 from both sides. Okay, and I get 52.5 equals 0.482x. So x is equal to 109 exactly. And I think I'm going to go back and multiply these two numbers again and carry out more decimal places. I think my calculator is set to not carry it out to too many decimal places. Oh well, I can't seem to fix that. Well, anyway, I get 109 because my calculator is chopping it off. I've just found how to fix it. All right, so I'm going to do it again. 106.905 times 0.5184. There we go. All right, so I'm going to write this down here, 55.4196. 55.4196. All right, so then we'll subtract from both sides. And I get 52.4486, and then divide by that 0.482. And I get 108.815. That's much better. 108.815. Now, what I just had to do with my calculator is a good example of get one calculator and use it, because should this happen on a test, either you don't know how to use scientific notation on a calculator you've borrowed, or I just had to fix the number of floating decimal places. Really better if you're familiar with, you know, one calculator. All right, let me get ready for the next one. Okay. All right, let's go back to the notes, and we're going to talk a little bit about chemical formulas. This really could be taken out of the lecture probably at this point, but it is important. I think we do have to talk about it because it involves moles. All right, so we know how to look at a chemical formula by this point and know the information that it contains. So I'm going to lead you through that idea down here. So in review, the subscripts tell us how many atoms of each element are present, and those numbers can be extended to such other counting units as the mole. And this relationship between numbers and formulas and later in chemical reactions comes up again and again. Numbers in chemical formulas almost always represent both the numbers of particles and the number of moles. And the same thing is going to be true with those coefficients in chemical reactions. This is not true of mass, right? While mass is conserved, the numbers in formulas do not directly extend to mass, but are connected through the mole. So we're going to go through this thinking here. If you had one water molecule, how many hydrogens would you have? 2, right? If you had 10 water molecules, how many hydrogens would you have? 20. So you're in your head, because, and I used water because it's such a familiar molecule, there are 2 hydrogens per water molecule. So you had no trouble with those 2 questions. Now we're going to change the counting unit. If you had a dozen water molecules, how many dozen hydrogens would you have? You would have 2 dozen. It's in fact 24 atoms, but I'm not asking that. I'm asking how many of the counting unit do you have? So in every case so far, you've multiplied by 2. If you had 10 dozen water molecules, how many dozen hydrogens would you have? You'd have 20, because you're still multiplying the counting unit by the subscript. Now we're going to go to the mole. If I had a mole of water molecules, how many moles of hydrogen would you have? 2. If I had 10 moles of water molecules, how many moles of hydrogen would you have? 20. Now here's a different question. If you have 5 moles of water, how many hydrogen atoms would you have? I am going to take this question and this next question into our writing, and we're going to talk about that, and then we'll come back and we'll pick up this practice, okay? Because I want to make sure that we understand how to put this on our chart, and then when we come back, we'll be ready to do that, okay, with our other, and I did miss that if, okay. So I'm going to put the chart down here, over here to the side, actually, mass, because I'm going to introduce one more piece to the chart. And we'll be doing that throughout the second half of the semester. We'll be introducing a couple more things. But as we get into chemical reactions in the next lecture, we are going in chemical reactions, we take things apart and put them together in new arrangements. So it's important that we understand how, as we count particles when we take them apart, how to account for that. All right, so if I have 5 moles of water molecules, I'm here. What we've just done with the previous questions is what I call up the middle, where I go from mole to mole, but I am taking it apart, so it's like the middle of the formula, and you're multiplying times the subscript, okay? So in all of our previous questions, we were multiplying all those counting units by the subscript. If I have 5 moles of water molecules, I would have 10 moles of hydrogen atoms. 5 times 2 is 10 moles. But I don't want moles here. The question's different. It's how many hydrogen atoms. I always think of the mole as like a bag, because I used to have a chem book that showed the mole like a bag. And in that bag is Avogadro's number. So anytime you want to know how many particles there are and you're in moles, either here or here, you're multiplying by Avogadro's number because you're like opening the bag. So in this case, after I multiply 5 times 2 to get 10, I am then going to multiply by Avogadro's number to get my answer. So it's 10 moles of hydrogen, which is then multiplied times Avogadro's number if I want to know the number of particles. All right, so that's atoms per mole, and I end up with 6.02 times 10 to the 24th as my answer. All right, so if you have moles of a compound and then you're asked about something inside of the compound, you go, quote unquote, up the middle, multiply by the subscript, and then if you're asked about how many particles it is, you've got to multiply times Avogadro's number. So, another question. If you had 10 grams of water, how many oxygen atoms would you have? So first of all, where are we starting? 10 grams of water. We are starting right here on the chart. And then I'm asking you about something inside of the formula. So you need to go from here to moles, and then up the middle to get the moles of oxygen, and then we can use the molar mass of oxygen to get that, to answer that question. There's another way we can do this with mass percentages, but we haven't learned that yet. So 10 grams of water, H2O, times 1 mole of water weighs, if you add them up, 18 grams, 2 hydrogens, 1 oxygen. All right, but then how many oxygen atoms in a water molecule? 1 oxygen, or 1 mole of oxygen, that looks like 10. So 1 mole of oxygen, this is what I'm doing up the middle, for every 1 mole of water. Okay, that was H2O. And now I can convert up here, and now I can multiply times the molar mass of oxygen to answer this question. So it'll just be 16 grams per mole of oxygen. Okay, so 10 divided by the molar mass to get to here, to mole, and then up the middle, subscript, which in the case of oxygen is 1 in the water molecule, and then times the molar mass of oxygen. So 10 divided by 18 times 16. And I have 8.9 grams of oxygen. Now we're going to learn in a few minutes, how to use mass percentages, and we could have done that. We could have taken the 10 grams of water times the percent of oxygen to answer that question. All right, back to the notes. Practice, right? So we've got some practice on this idea of up the middle. Oops. Get it all. All right, here we go. And real quick, mole chart. Mass, mole, particles, and then up the middle. I don't think we're going to need much more than just looking at formulas and subscripts. How many moles of oxygen are in 12.4 moles of iron 3 nitrate? Now, I used a complicated formula on purpose. How many oxygens are in this formula? So that's the first thing you have to ask yourself. When you are asked about something inside, look and see how many of those things are in the formula. 3 times 3, there are 9 oxygens in this formula. And all it wants me to do is to go from 12.4 moles of the compound to moles of oxygen. So I'm just going to multiply 12.4 moles of the compound, iron 3 nitrate, times 9 moles of oxygen for every mole of the compound. We'll just do that, okay? So 12.4 times 9. So up the middle, something inside the formula. It's 111.6 moles of oxygen. Now if I'd asked how many oxygen atoms are in 12.4 moles, I'd start here, go to here, and then open the bag or multiply times Avogadro's number. But it asked how many moles. So all you have to do is go one step. Number 2, which sample contains the greatest number of moles of chlorine? So we're staying in moles. So all we're going to do is take the number of moles of the compound times the subscript, okay, for chlorine. So why don't you give this a try, stop the video, give it a try, and come back. All right, I'm going to put the answers out to the side for each one of these. All right, so 3.8 in A is 3.8 times 1. 3.4 in 2, 1.7 times 2. In C, it is 4.2 times 1. There's only a 1 there next to the chlorine. And then in D, it's 2.2 times 2. Remember, we're just looking at chlorine. So that's 4.4. So the answer is D. Okay. Next one, determine the number of moles of hydrogen in each sample. So again, you are looking at something inside the formula. So you ask yourself, if I had 1 water, how many hydrogens would I have? 2. So you're going to multiply that counting unit times 2. And you're stopping at the moles. You don't have to do anything else. So 4.67 times 2. 9.34 moles of hydrogen. And that'll be moles of hydrogen in each case. And then B, it's going to be times 3. So 25.2 for B. And C, I'm going to be multiplying times 4. So 0.468 moles of hydrogen. And D, 35.8 times 22. So 787.6 moles of hydrogen. In every case, if the question had been how many atoms of hydrogen, the next thing you would do would be to open that mole by multiplying times Avogadro's number. All right, let's go back to the notes. Let's see what else we've got to learn today. Mass percentage. It is just a percentage, and percentages are always just part over the whole. So you're going to take, so if I want to know the percentage of hydrogen in water, I'm going to take the mass of hydrogen, that part of the formula, and I'm going to divide it by how much the whole thing weighs times 100. For oxygen in water, it's the oxygen part over the total times 100. So that's pretty easy. Another way to approach mass percentages is from real data. So if you had a 2.5 gram sample of some compound, okay, and you knew that it contained 1.44 grams of carbon and 1.06 grams of hydrogen, the whole part is how much the whole sample weighed. The carbon part is the 1.44. You're going to get the same answer as if you had a formula and you did it from the formula, okay, if the compound's the same. So carbon part over the total, hydrogen part over the total times 100. All right. Of course, for the second one, or if you had a third one, you could always subtract. For the last one you have to figure out, you can always subtract what you've got so far from 100 to get the last one. So let's take these 4 into our notebook and work on those. And then when we come back, we have one more thing to learn today, and that is empirical formulas. Okay, so we're going to get the percentage composition for a hydrocarbon. Ooh, let's make that bigger. Hold on a second. Let's make it... No, then it goes off the page. Let's go full screen. There we go. All right, so we're going to calculate the percent composition, and you're given a formula. So the first thing you've got to do is get the total. So you're going to add these up, 8 times carbon's weight plus 18 times hydrogen's weight. Okay, so 8 times. And when I add up those, the total is, when I add up the carbon and the hydrogen part, it's 114.26. All right, so the percent of carbon is the carbon part, which is 8 times your 12.01 for carbon. So I've got 96.08 divided by the 114.26 times 100 to get the percentage of carbon. And that's 84.1%. Now if I wanted the hydrogen, I could take the 18.18 divided by the total, or subtract the 84.1 from 100. And the hydrogen part should be 15.9. So this is pretty easy. All right, why don't you stop and try number 2. You've got 2 different compounds. You've got, and we're only doing oxygen, but you have to get the whole, the whole mass first. All right. All right, so I'm going to write down some of the total here. In fact, I'm going to go ahead, since I know the masses for this one. The oxygen part's 32. The total is 44 times 100. And I'm only rounding here as much as I always do. I always put carbon in pretty much as 12 and oxygen is 16. So I get 72.7% oxygen. Now for this next one, it's a lot bigger. Oh, we got 3 of them. We are going to, I know that 3 oxygens is 48. So then I got to divide by the total, which is going to be big, 17 times. And when you get something big like this, I will carry them out a little bit more. So I'm going to put down here at the bottom, and just so I don't lose it, what I'm getting for each element. So that's carbon, hydrogen, I always use 1.01 for hydrogen, nitrogen, and then the 3 oxygens. Okay, so I'm going to add all that together. That gets me 285.36. So it's 48 over 285.36 times 100. And I get 16.8% oxygen. On the real page. Okay, 16.8% for B. So I'll put that down here. 3B, 16.82%. All right, 3C, since I ran out of room up there, I am going to really big molecule, digitoxin, another drug, morphine, of course, being one as well. I'm going to take 13 oxygens first. And that's 208. So it's 208 over 208, the oxygen part, plus hydrogen, plus 12.01 for carbon times 41. 492.41 just for the carbon. Okay, times 100. So my denominator was 765.05. 208 divided by 765.04. Yep. Equals times 100, 27.19%. 27.19% oxygen. Alrighty. Number 3, silver chloride, often used in silver. Oh, it wasn't 3B, that was 2B. Sorry about that. 2. All right, number 3. Silver chloride, often used in silver plating, contains, hard to say, 75, I believe, 0.27% silver. Calculate the mass of silver chloride in grams required to make. Now, this is the kind of problem that drives students crazy, okay? So, you are being given a mass percentage of something. The first thing you need to do before you get that deer caught in the headlights look is write down what a mass percentage means. All right, so this is number 3. So, a mass percent, any percentage, is equal to the silver, since this is silver part over the total, times 100, total mass. And let's check off what we have. So at least you've got a formula written down. And now you can go back and plug in the numbers you're given. Well, you're given the mass percentage. It says calculate the mass of the silver chloride in grams required to make 4.8 grams of silver. So the silver part you have, it's 4.8, and this is the part you don't know. All right? So I have 75.27 equals 4.8 over x times 100. All right? So if I take the 100 to the other side, 0.7527 equals 4.8 over x. Cross multiply and divide, and essentially you're going to take and 4.8 and you're going to divide by 0.7527. And you get 6.38 grams, all right, for 3. So write down the expression and then start checking off the things you know. All right. Do some erasing for number 4, or extend my page a little bit. There we go. 37.5 grams of copper 2 fluoride contains 14 grams of fluorine. What is the percentage of copper and fluorine in the compound? All right, well, here's your total. Here's the fluorine part. So let's do the percent of fluorine first. Percent of fluorine equals fluorine part, 14 grams, divided by 37.5 times 100. All right. So 37.3%. And then the copper part, we can just take that 37.3 and subtract it from 100. $62.7. So percentages, you're in college, you need to be able to do percentages. All right, going back and learning how to do empirical formulas, and then that will finish up lecture 4. All right, what is the problem? I guess I gotta get out of this. That's the problem. All right, empirical formulas. It's a procedure. Now, it is the simplest formula, the simplest ratio of subscripts, essentially. So for the compound benzene, which has the formula C6H6, the simplest ratio is CH. Okay? So that would be, CH would be the empirical formula. The formula and the mass are related by the same factor. All right, so I take this factor, multiply it times the formula, I get the molecular formula. I take the exact same factor, multiply it times the empirical mass to get the molecular mass. So in the case of this molecule, since we know both the formulas, we see that the factor is 6. The empirical mass for benzene is 13. 1 carbon plus 1 hydrogen. 13 times 6 will give me the mass of the compound. So sometimes we know one, we don't know the other, but the factor is going to enable us to get back and forth. All right? So talking you through that, what I just said, right here in this short paragraph. All right, now here in bold are the 4 steps for how to do empirical formulas. We can use mass percentage data, or we can go directly from experimental data to get to an empirical formula. So the first thing you're going to do is convert the mass, whether it's given in experimental data or as a mass percentage, to moles. So convert to moles. Then you're going to take the smallest number of moles that you have, because you'll have multiple elements, and you're going to divide all of them by the smallest number. Number 3, if the numbers you get are not whole numbers, we can use a multiplying factor. You'll see it's kind of a hit and miss thing. You'll see as we do some examples. Often this produces the molecular formula. If the molecular mass is known, then I can use the empirical mass to get the molecular formula and so on. So you will see these are the 4 steps. Really, it's just 1 and 2. 3 and 4 take it a little bit farther. So let's take our so here's an example, walking you through it, and then there is another example walking you through it, and then we'll do 2 ourselves. All right, so let's walk through these together. So I'm given some grams. It looks like this is lab data, and I want to know what's the empirical formula. So I'm going to take the grams of selenium, convert to moles. Grams of fluorine, convert to moles. When I did that, the smallest of these 2 moles is the selenium. So I'm going to divide the selenium moles by itself and the fluorine moles by the selenium. This is what you're doing when you do this, is you're setting the small one to 1 so that its subscript is 1. So subscript for selenium is going to be 1, and when I divide the fluorine moles by the selenium moles, I get a 6 for fluorine. So here's your empirical formula. 1 for selenium, 6 for fluorine. You're done. Didn't ask you to do anything else. Here's something a little more complicated, but you're going from a mass percentage. No different in your steps. You take the percentages and you assume you have 100 grams of the compound so that those percentages become mass. So for carbon, you have 37.51 grams. For hydrogen, you have 4.20 grams, and for oxygen, you have 58.29 grams. Convert them all to moles using the mole chart in your periodic table. This is what you get when you convert them all to moles. Carbon is smallest. You're going to divide them all by carbon, so that carbon is 1. When you do that, you get 1.33 for hydrogen and 1.16 for oxygen. These numbers aren't so clean. So you search for a number that you can multiply this number and this one by, so that when you multiply by the same number, you get a whole number. So let's start with 2. I think you can see that if I multiply 1.33 times 2, I'm not going to get a whole number. Since 1.33 is close to 1 1/3, let's try 3. If I take 1.33 times 3, I end up with 4. But 1.16 times 3 gives me 3.5. So let's try 6. 1.33 times 6 is 8. And 1.16 times 6 is 7. So that's going to be our factor that we're going to multiply so that we get nice whole numbers. But I have to multiply them all by 6. So C1 becomes C6. 1.33 times 6 becomes 8, and 1.16 becomes 7. And this is your empirical formula. And for this compound, this actually happens to also be the molecular formula, which is what I said up there in step 3. All right, let's do 2 examples together to finish off lecture 4. And then next lecture, stoichiometry. And if you took it in high school and your teacher scared you to death with how hard it is, I think you're going to find that my approach is a lot easier. All right, here we go. Mass percentages first. You've got a sample of nickel that reacts with oxygen, and so here is your, and so you get 2.852 of the metal oxide. So you've got your grams of nickel. You're going to have to subtract the total from minus the nickel to get the oxygen. So you've got, for number 3, you've got 2.241 grams of nickel, and we're going to convert that to moles. All right, using what's on the periodic table for nickel. 1 mole of nickel is nickel, 58.69 grams. Now, to do oxygen, I need to take the 2.852, oops, I'll write it there. That's where I need to write my moles of nickel. So for the oxygen, I'm going to take 2.852 minus the 2.241 to get oxygen grams. And that's 0.611 grams of oxygen, and then convert it to moles. Okay. I get 0.0382 moles of nickel. And I get 0.0382 moles of oxygen. So they're exactly the same. So my empirical formula is going to be NiO. Because if I divide them both by 0.0382, excuse me, I end up with 1s for both nickel and oxygen. And knowing nickel the way I do, it usually forms a +2, so this makes sense that its formula would be NiO. All right, number 4, caffeine. And this time we're going to go from empirical mass data. So I'm going to move this over just a little bit so we can see all of the information. All right, and we're going to have to take it a little farther because they gave us the molar mass and they want to know the molecular formula. But let's do one thing at a time. So number 4, we're going to go with 49.48 grams of carbon. And we're going to convert it to moles. Okay, we're going to take 5.19 grams of hydrogen, and we're going to convert it to moles. Okay, we're going to go with 28.85 grams of oxygen. Convert it to moles. And then our last one is, oh, that was nitrogen. I do that every time. So let me fix that. And it's 14, not 16. So this is nitrogen, 14. And my last one is oxygen. And 16.48 is my amount. And I just needed to keep that up just so I could see it. 16.48 grams of oxygen times 1 mole of oxygen weighs 16 grams. And I will fix this up here. It's nitrogen, not oxygen. All right, so now do all the divisions and get your moles. Okay, I got 4.120 for oxygen, carbon. .14 moles of hydrogen. 2.061 moles of nitrogen. And I get 1.03 moles of oxygen. So oxygen is my smallest. So I'm going to divide all of them by oxygen's amount, because it's the smallest. And this is going to give me my subscripts. Okay, so 4.12 looks like it's going to be 4 carbons. All right, looks like 5 for hydrogen. Looks like 2 for nitrogen and 1 for oxygen. So my empirical formula is C4H5N2O. All right. Now, it wants us to determine the molecular formula, but they gave us the molecular mass. So let me extend the page and remind you of what we said at the beginning of the notes. If I take the empirical formula, which is C4H5N2O, and I multiply it times the factor, I end up with the molecular formula. All right? Well, I have too many unknowns here. I know this, but I don't know this or this yet. I am going to use the other relationship that says the empirical mass times that same factor will give me the molecular mass. And I have 2 of those. I've got empirical mass because I can add up all the values in my empirical formula, and they gave me this. It was 194. So I don't know my factor, but I'm going to add this all up now, my empirical mass. So 4 times carbon, 48, plus the hydrogens, plus the 2 nitrogens, plus the oxygen, and this is 97.1, the empirical mass. So if I take 994 and divide by 97.1, I will have my factor, and it's 2. So X is 2. So put that in here, now that I know it's 2, and I'm going to multiply everything in the empirical formula by 2. So my molecular formula is C8H10N4O2.